most folds do occur with shortening or compression, right? So we see the folds here, anticlines and synclines. We could have shear forces that can develop some folds. So here's, a shear fold. We could also generate folds at convergent margins where crust is forced over the top of other crust. Later on, when we talk about this place called the fold and thrust belt, which occurs on the back sides of mountain belts. And so here because we're having compression going on, making a mountain over here, we're going to force this strata out, and it's going to override younger strata, right? So the older strata will override this younger strata here. And then I mentioned how we make the monocline. So here we have a pre-existing older fault with some strata sitting over it, but then we reactivate this fault and we have the monocline. That talks about tectonic foliation and cleavage. And for undeformed rocks, sand grains, conglomerates are all going to be pretty spherical. And the clay will pretty much be parallel to the bedding plane, because remember, clay, because it's so fine grained, you don't see cementation. Clay has to maintain its lithification just from compaction alone. So the clay flakes are compacted parallel to the bedding plane, right? But during deformation, in this case, we'll look at ductile deformation. We'll see the fold here, right? And we'll see that the sand grains are now inequant. They're either cigar shaped or elongated. They've changed. And note that the clay flakes are either going to experience neocrystallization, where they form new minerals, or they're going to all align themselves to this new deformation foliated plane, right? And so here's our cleavage plane right here. So I also note that the cleavage plane is not parallel to the geologic beds, right? So clay at angles to bedding, and also the cleavage plane at angles to bedding. And that your book mentions in upper state New York, and you can see that there's relic bedding going on here. But you can see that there's a strong pervasive cleavage or foliation that develops here, right? And the rock is fracturing preferentially along those cleavage planes instead of the bedding plane. And so that's just an idea of this cleavage going on and how that develops with this deformation. Mountain building and the term called orogenesis or orogens. And orogens is basically a mountain genesis, the birth of a mountain. And usually, like I said, it's primarily at convergent margins where you're seeing this. You could also see them at divergent rift margins as well. At a convergent margin, this is a subduction zone. And so we're seeing an ocean to continent convergent margin. We see the accretionary wedge. And one interesting thing that happens here is that you get these accretionary wedge slices that occur here. And you can see that as I subduct material here, I'm going to push younger material underneath older material. So usually in these accretionary wedge slices here, older rocks appear here, younger rocks appear here, because right now we're actively pushing new material under here, but the older material is being shoved aside. So that's one of the unusual features of an accretionary wedge. Here we have an ocean plateau or an island arc that's too buoyant to be subducted. So when this enters a trench, instead of being subducted, it's going to be accreted. It's going to be attached to the continental margin here. And we're going to call this an exotic terrain, or sometimes we call these tectonostratigraphic terrains, but it's going to get accreted. So as this terrain gets accreted, attached to the margin, the subduction zone will no longer be here. It's going to move outboard or seaward side of this accreted terrain. There'll be subduction zone out here when this gets accreted. So that's one key thing. Subduction moves seaward side of the accreted terrain, so oceanward side. The thing is, uplift usually occurs on the overriding tectonic plate. So we got the downgoing subductive plate, and this would be the overriding tectonic plate. And that's where the uplift is going to occur. And uplift is a general word we use for the vertical tectonic movement of rocks, uplift. And in this case, it's through compression. Fold and thrust belt. So your book makes a pretty big deal about this fold and thrust belt. And it doesn't use the word hinterland, but the thrust belt always occurs in the hinterland. And the hinterland refers to the back arc, the regions behind the main convergent margin over here. And then we do see these thrust slices, right? And what's going to happen here is these thrust slices will be pushed over the top of this detachment fault. So the detachment fault is a long fault upon which these thrust slices move up over. And note that opposite to the accretionary wedge, here I'm going to take the older rocks and push them up over the younger rocks. Here I take young rocks and tuck them underneath the older ones, right? So there's something else going on here where I take these, for example, this brown color is Proterozoic rocks, and I'm going to push them up over these Paleozoic rocks. So I'm taking older rocks and pushing them over younger rocks. That occurs in the fold and thrust belt behind the orogen. So this would be the orogen or the mountain that's being formed here. In this example, we got a continent-to-continent convergent margin. So now, the key thing about a continent-to-continent convergent margin, like the Himalaya range or the Alps are formed because Africa and Europe are colliding. So what happens in this case is we're going to see two fold and thrust belts, right? A fold and thrust belt on either side, right? And then the main range being pushed up. The North American Cordillera and the accreted terrains that occur over here. So remember, these are too buoyant to be subducted. And so there are many in Alaska going down. In fact, California, the Sierra Nevada, there's many accreted terrains in the western foothills. And many of those are where the California gold originated. Well, how do we know the rates of mountain building, of orogeny? How do we know this? And we do it by investigating, doing field data, collecting fossils, kind of like what Wegener did, right? Kind of trying to figure out, using all the tools necessary, not just in geology, but also in biology. But now in the 20th century, 21st century, we have global positioning systems, GPS, and we have a bunch of meters measuring the rates of tectonic uplift. One thing about handheld GPS meters, they have an accuracy of about 2 meters. So you can get within 6 feet of your point, which is awesome. However, the research grade GPS sensors that we use have an accuracy of 2 millimeters, which is basically the thickness of your fingernail on your thumb. So they can get that accurate. So they can really measure how fast these tectonic plates are moving. And for the Andes Mountains, they're rising at about 2 centimeters per year. How can you make these mountains? Because remember, mountain building and erosion work simultaneously, right? So what goes up must come down is a section in your book. And so erosion, glaciers weather this stuff down, rain. So in order to have mountains to continue rising, the rate of uplift must exceed the rate of erosion. So rate of uplift exceeds the rate of erosion, forming the Himalaya range and then this Tibetan plateau back here. One thing that happens is because we do have these crustal roots that develop, right? So we have these very thick crustal roots. Sometimes the crustal root gets so thick that part of the lower lithosphere, the mantle lithosphere, delaminates and sinks back into the mantle. So delamination can change things. And when you delaminate this denser peridotite mantle here, what happens is a sinus moves in here and it's warm and buoyant, and it can cause uplift through making a plateau, like the Tibetan plateau. Other things you may see is, because we see decompression melting, you may see magmas come up here and melt crustal rocks in here. So you might see some crustal melting going on there as well. Now, other mountains that can form, here's an example of mountain ranges that are forming via tensional stress, right? Tension is stretching. And so we call these fault block mountains. Often we call them basins and ranges. We use a word called graben. I'll talk about grabens. A graben is basically it means ditch in German, but it's a down-faulted basin. So these would be grabens in here, and the ranges are the horst. So a horst would be the range, and the graben is basin. So we have a horst and graben topography, and this is very typical of the western United States. From basically the Sierra Nevada all the way out into Utah, we have a region called the Great Basin, and it's characterized by basins and ranges. So geologists call it the Basin and Range Province, which is typical of these horsts, which are the mountain blocks, the fault blocks, and the grabens, which are the basins. one of the questions is asked, well, are there any sediments related to orogeny? Well, yes, you get igneous rocks, you get metamorphic rocks, but then we have these mountains, so there's erosion. So you get alluvial fans, you get sedimentary basins, you see deltas. And example here, these basins develop because this mass is a heavy weight here, flexing the lithosphere, allowing basins to develop. Now, this concept of isostasy, this is an important one, and explains why continents float higher on the asthenosphere. So think about floating blocks. A bigger block tends to float higher than a thinner block, tends to sink lower, right? And so, and that's kind of the idea. Lithosphere floats on the softer asthenosphere, right? So as I add more material by thickening, shortening the crust here, thickening, I need to develop a crustal root into this softer asthenosphere so I can float this lithosphere higher in elevation. So kind of the analogy are these wood blocks. In order to have these mountains, I need, at high elevations, I need a bigger mass underneath them to buoy them up. The elevations that we see on Earth's surface represent a balance between the buoyant force, right, of this block floating on the asthenosphere and the force of gravity that pulls it down. And we call that isostatic equilibrium, right? So also one thing we want to mention with continental rifting is, yes, we're pulling apart and we're dropping these fault blocks down along another detachment fault that occurs here, but this detachment fault allows the sliding of these blocks to slough off here. But because we're stretching and thinning the crust, we allow a asthenosphere to move up, and the hot asthenosphere is going to make this area rise so we can actually lift some of these mountains and actually create mountain ranges. For example, East Africa, in the East African Rift, where Africa is basically rifting away from Somalia and Ethiopia, we have big volcanoes like Mount Kenya and Kilimanjaro form in this valley. There's a term called orogenic collapse. At some point, we'll get the mountain so high that it becomes gravitationally unstable, and we start seeing these blocks start sloughing off. Sort of the analogy here is, here we have some cheese left out in the sun, and the cheese starts to founder and kind of slough off because of this heat. One of the questions asks, why can't mountains get much higher than Mount Everest? A little over 8 kilometers high, 29,000 feet. Now, the reason is because Earth has a high heat flow. In other words, as you go deeper in Earth, the rocks start to behave ductily, especially the asthenosphere, and begin to flow and move out of the way, which will eventually result in collapse of the orogenic system here. This next section of your text discusses this idea of a craton, and the craton are the stable interiors of continents. Other things, cratons are very old. They've experienced episodes of metamorphism, orogenesis, erosion. But the craton is really separated into two areas. One is called a shield, and the shield would be the exposed Precambrian older rocks, right? So Precambrian older rocks, that would be the shield here. The platform is covered by younger sediments, usually Phanerozoic sediments, Paleozoic, Mesozoic, Cenozoic. So here's the platform. Under these sediments, you would find the Precambrian rocks. So that would be the Precambrian shield you find there, the craton. Here we see Precambrian shield exposed. Here we see a platform covering the sediments. And I mentioned earlier these structural basins and structural domes. For example, if we look at the ages, note the Precambrian rocks are these purple ones here, right? And then as we go over here, we have younger rocks. This pink rock is Ordovician. The blue rock is Mississippian. So around this Precambrian rock here, I see old Precambrian rock surrounded by Cambrian rock, by Ordovician rock, by Mississippian rock. So this is showing me that this is a structural dome, the Ozark Dome. Whereas Illinois, the whole state, is a basin. I have younger Pennsylvanian rocks here, and then older Mississippian rocks around it, right?